Okay, you can start.
Okay, so I really pushed to introduce this speaker. I couldn't miss the occasion because it's such a great pleasure and honor to have known Jouko Väänänen for who knows how many years now, to have co-authored 3 papers with him, and to have known him mathematically and personally. Let me tell you a bit about him for those who are probably very few who do not already know who he is. He is a Finnish mathematician. He has spent almost all his career in Finland, although his PhD comes from Manchester. He got his PhD in 1977 with Peter Axel, but this somehow he got the PhD with many people. He traveled throughout Europe during that time, including going to Poland and working with Mostovsky. So already at that age, he was a very broad mathematician, and his career has been in model theory, set theory, philosophy, and also theoretical computer sciences. So his work includes abstract model theory that is quite close to some of the work of Michael Mackay, who spoke as the first speaker. His work, Jouko's work, is very much about use of games. So many of his papers are about use of games in model theory and in other contexts. But of course, as I said, he also has publications such as philosophical publications in the most prestigious philosophical journal, which is Synthèse. He also has a very long CV from the point of view of being engaged in the mathematical community. He was the vice rector at the University of Helsinki. He was a member of the executive committee of the EMS, treasurer of the European Set Theoretic Society since 2007, advisor of many students, the father of what you could call the Finnish School of Model Theory, and of course the author of many interesting papers and 2 books, Dependence Logic, which is a logic that he introduced, and Models and Games. And finally, let me say that there is also a book about Jouko. That is a book that came out of a conference that his colleagues organized for his in honor of his 65th birthday. It's called Logic Without Borders. And this title is very well chosen because the work of Jouko Väänänen is really logic without borders. So I'm very pleased to be able to introduce his talk, which is entitled The Strategic Balance of Games in Logic. Thank you.
Thank you, Mirna, for your nice and kind introduction and for the invitation to speak in this seminar. So now I'm going to share screen. Let's see what happens. Okay, I assume you see, and then you will complain if you don't. Okay, the strategic balance of games in logic. It's I'm presenting a kind of view of games in logic, and by doing that I present a view of logic, and I thought that this rather general approach is appropriate for this interdisciplinary seminar. So I already say in the beginning that my talk may be a disappointment from the point of view that all the results that I'm talking about, methods, are from the late 60s or even 50s or early 70s, although there is a lot of work on this field also today. But I present a kind of a position or view. So here's another view about chess. Thomas Huxley, the chessboard is the world. Okay, so this is maybe a little bit strong statement. I am also talking about logic, and I'm not saying that the chess is logic or logic is chess, but it's that games really govern logic. Okay, so I'm talking about 3 games, and I'm happy to say that I learned about these games from papers of Michael Mackay, who seems to be in the audience. And so the games are evaluation game, model extents game, and the Ehrenfeld-Freisse game. And I'm going to argue that these really are just like one informal or one yes, like informal game, which is essential to logic, and it is sort of behind, well, elementary logic, whether mathematical or philosophical, but also it goes can be quite technical and goes deeply into model theory and set theory, and maybe even proof theory. So if I compare logic to fields such as algebra, topology, analysis, and so forth, I think that this thinking behind this informally defined game, which here takes the form of 3 different games that I'm going to talk about, is really what distinguishes logic. And like in all these areas, algebra, topology, analysis, you develop a kind of way of thinking, of course methods also. And I think that this game or these games are the thinking which characterizes logic and distinguishes it from others. And I'm trying to argue that they are very closely related, and this is the strategic balance, the pillar on which logic stands. More technically, I'm going to talk about game which is behind truth, in a sense, another game behind consistency, and another behind formula. And I mean, these are, in a sense, basic things in logic, and I define these translations between these games, which translations of strategies, and which I argue that establishes the close connection between these games, and that there's really like one game behind all of them. Okay, so the evaluation game, which is also known as semantic game, let's jump into that first. So there are 2 players, Abelard and Eloise. I use these names, I think, introduced by probably Hodges. So there's a sentence and there's a model. And then we look at subformulas of the sentence and assignments in the model. And a pair of a subformula and an assignment is called position. In the beginning, the position is just a sentence and an empty assignment. Then whenever I have an assignment, I take this technical auxiliary concept of the diagram, is a set of literals, sort of atomic and negated atomic formulas that the assignment satisfies in the model. I assume that formulas are built from conjunction, disjunction, universal extensor quantifier, and negation, but formulas are for simplicity in negation normal form, so negation is only in front of atomic formulas. And in this game, which I now describe intuitively, Eloise defends the proposition that phi is informally true in the model, and Abelard doubts it. So here's a game. So we are in a position psi s. Psi is a subformula of phi, and s is an assignment in the model M. If psi is a literal, the game ends, and Eloise wins if psi is true. It's an element of this diagram, and otherwise Abelard wins. So when we come to the atomic things, then we look at what the model says. In fact, you can identify the model with this diagram if you don't like models. Okay, if the position is conjunction, Abelard chooses which is a continuation. If the position is disjunction, Eloise chooses if the position is universal quantifier, Abelard chooses an element which is then used in the assignment as a value of x. So this means an assignment where x has been changed to a. And if it is an extensively quantified formula, then Eloise chooses the element and the next position is this. So there are these two types of moves: connective or conjunction or disjunction, or universal or extensile quantifier. And the only difference in the action is just who chooses, Abelard or Eloise. And then it is determined what the next position is. It's very, I would say, basic, very basic game of this type, two-person perfect information zero-sum game. Okay, now we say that phi is true in the model if Eloise has a winning strategy in this game. And this is what is known as the game theoretical meaning of truth in a model. And of course, there is also the Tarski inductive definition of truth, and this is equivalent to it. But if wanted, we can simply take this as definition of truth, what it means to be true, that Eloise has a winning strategy. So then this gives, in a sense, a meaning of truth in a model. But we can go actually further and say that the game is the meaning of phi. So not whether one has a winning strategy or not, but simply the game is the meaning. So then the meaning would be a broader concept than mere truth or falsity of phi. But I'm not going deeper into this. This is more like so-called game semantics, while this is more like what is called game theoretical semantics. Anyway, the idea that you can define truth in this way, I think is has been mostly advertised or promoted by Hintikka starting 1968. And he refers to Henkin, who defined this game for quantifiers. And Hintikka also refers to Wittgenstein's language games as his inspiration. And okay. Now, the important thing about this game is that you can see a lot about both the model and about the formula in this game. So the game reflects the syntactical structure of the sentence pretty perfectly. So the game for the conjunction is, you can build it from these two games for the conjuncts, same disjunction, extensor, and universally quantified sentences, which is sort of related to compositionality. On the other hand, if you have some structure for the model for the product, the sum or reduced product can be reduced, is intimately related to the original games, as shown by Pfefferman. So both on the structure side and the sentence side, this game reflects whatever structure there is. Moreover, if phi happens to be propositional, so no quantifiers, then in this game, of course, we can forget these cases 4 and 5, and we have a kind of a new game for the propositional. If phi is universal, then we can forget the universal quantifier move. If it is extensile, we can forget the extensile move. If it is universal extensile, then all universal type moves come before extensile type moves, and so forth. So we can make this game to reflect the structure of the formula. Moreover, we can add new logical operations, and this is what I think was most interesting to me when I was a student or young. We can add these infinite conjunctions, disjunctions, generalized quantifiers, higher order quantifiers, and in this case, it is usually pretty clear how to define this game, how to accommodate the new logical operations to this game. For example, if we look at L infinity omega, if we have an infinite conjunction, it's really the same. Abelard chooses the index, and the next position is the appropriate formula with the same assignment. If it is a big disjunction, the only difference is that Eloise chooses from a bigger set than the next position is. And for generalized quantifiers, it's a bit more complicated, but it is pretty obvious how it is done. In modal logic, we can also do this. So here we work in a Kripke structure, and we follow the accessibility relation. And instead of quantifiers, we have this like box, and then Abelard chooses the next node according to the accessibility, and if it is diamond, then Eloise chooses. In fact, oh, sorry, where am I? Here. I think Hitika first thought about this in modal logic, hanging with quantifiers, and more difficult to say. Moreover, this game is a very useful tool in finding countable submodels with interesting properties. So, for example, if Eloise has a strategy tau in this game, and we take all submodels which are closed under the function, which are closed under the strategy, then the strategy of Eloise is also a strategy in the game in the smaller structure that we obtain in this way. And it is a winning strategy if the original one was. So in this way, we get a very nice formulation of Leeuwenhaen's column theorem, the first mathematical result in logic, that this set of these countable submodels, in fact, it is a club. It contains a club. So it's by result of Kicker. So it is a very strong, using this strategy in the semantic game, we get a very strong form of the Leeuwenhaen's column theorem. So I started with this evaluation game, and I think that it's a very versatile tool for understanding the meaning of a logical sentence in a mathematical structure for a big variety of sentences in different logics. And there is really, whichever logic you come up with, I think personally, I think that's a good idea to look at this evaluation game for that logic and see whether you see there like new features or whether some features are not analyzed properly. And all the while, it is perfectly recognized that there is also the inductive methods. Of course, inductive methods have a close relationship with game methods, as has been shown first by Moskovakis, and then, for example, by Spector, and then by Peter Axel, who was my supervisor in Manchester. Okay, now the second game, model existence game. In the previous game, we had a model and a sentence. Now we have just a sentence. In a sense, we have lost the model. We don't know the model. So now what we can ask when you don't have a model, you can ask about consistency or contradiction. So the question that this new game analyzes is whether there is some model such that Eloise can win the evaluation game. Again, we assume negation normal form and the first order operations. We have two players again. This is very much like the evaluation game. Intuitively, Eloise defends the proposition that phi does have a model. She might even know a model, but anyway, Abelard doubts it. And Abelard expresses his doubt by asking questions. Now, to talk about the hypothetical model, which maybe exists, maybe doesn't, we adopt an infinite sequence of new constant symbols. And here's a game. It's very much like the evaluation game. So there are very similar moves, but the difference is that rather than having just one pair as a position, we have a finite set of pairs for the position. So the fact that instead of one pair, we have this finite set that corresponds to the fact that we don't actually know a model, but we are contemplating on possibilities, and this finite set represents contemplation. So during the game, a position is a finite set of such pairs. In the beginning, it is just a singleton set with phi and the empty assignment. And whenever we have a position S, Abelard chooses a position, a pair from there. If it is conjunction, he chooses how we continue. If it is a disjunction, Eloise chooses how we continue. If it's universal quantifier, Abelard chooses how we continue. And if it is extensor quantifier, Eloise chooses how we continue. So it is exactly the same format of moves as in evaluation game. The difference is that we have this on the table, we have several possibilities. And if at some point we have a set which has a contradiction of both psi and not psi, then Abelard wins and it ends. Otherwise, the game may continue infinitely long. I think basically this was first presented by Beth, 55. He refers to Gentzen as his inspiration, Gentzen's natural reduction, which is a kind of a proof-theoretic analysis of our semantic thinking. Hindika, in his doctoral thesis in 55, he presented this method. Smalian, 63. So Hindika was, Beth and Hindika were like first order, like propositional logic, modal logic. Smalian first order logic, Mackay in infinitary logic, where this method became very important and where I also learned from Mackay's papers this method. And it is very nice tool for proving individual results such as interpolation theorems, completeness theorems, preservation theorems, and so forth. It's a kind of a tool. Okay, but let's see now what we can say about this. First, a sort of a trivial observation that if we have already a model, then the sentence is consistent in the sense of this game. But anyway, it's good to check this rather trivial thing first. So if we have a model M and Eloise has a strategy tau, that determines a strategy of Eloise in the model extents game. And if the strategy was a winning strategy, so then is this strategy in the model existence game. So Eloise can defend consistency if she actually has a model. So this is how it is done. I will skip this because it is rather obvious. So let's then look at the more interesting, especially historically more interesting direction. If we don't have a model, we really have lost the model, and we are at the uncertainty whether model exists. So how can we get a model using this game? So every strategy tau of Eloise in this model existence game actually determines a model and a strategy of Eloise in this evaluation game. And if this strategy was a winning strategy, then so is the strategy in the model existence in the evaluation game. So if intuitively this means that if Eloise has a systematic way to defend the consistency, then it can be, this systematic way can be can be translated with this translation psi into a winning strategy in a particular model which we obtain. So tau can be mapped into a model and a strategy. This was Beth's tutor Beth. So let's look at the proof. So this is not, as I said, a new proof. This is the old proof, but over the years it has maybe been streamlined. So the trick is to let Abelard play against Eloise, a kind of a complete universal strategy called, I call it enumeration strategy, in which Abelard really tries every possible difficulty that Eloise might have. So if during the game the position has a conjunction, then Abelard has some bookkeeping way to make sure that he eventually plays both of these conjuncts. If there is a disjunction, the position then at some point he will ask Eloise to choose which of these we continue with. For universal quantifier, he will make kind of a bookkeeping so that he will put this constant Cn to x at some point, and if it is extensile, then and at some point he will ask Eloise to put to choose the constant. So this is the kind of the most demanding strategy. And if we play so that Eloise plays her strategy tau, and Abelard plays this enumeration strategy, we get a kind of a generic sequence. In fact, this is a little bit like forcing or like bare category theorem argument. We get this generic sequence, and from this sequence, which comes from playing the enumeration strategy against the Eloise strategy, we get a model in a kind of canonical way, a little bit like in a usual proof of Gödel's completeness theorem. And the strategy of Eloise in this new model is that she makes sure that if the position at some point is psi s, then psi s belongs to this sequence. Okay. Now, so this can be used as a model construction, as I said. In fact, you can think of this, and I think this was originally the idea of maybe Beth, but I think certainly Hintikka, to replace talking about models by talk about this game. So if one doesn't somehow like the somewhat set theoretical approach to models in logic, one can avoid it by this way to some extent. Okay. Now, just as in the case of evaluation game, there is the inductive method called Tarski truth definition. Here is also an alternative formulation of this, is the concept of so-called consistency property introduced by Smalian, which is really one way to just describe the winning strategy of Eloise. And in some cases, it's more convenient to use a consistency property. In sometimes it's more convenient to use a moral existence game. They are really like alternatives. Consistency properties became very popular in infinitary model theory, and I think Mackay's probably doctoral thesis was the beginning of this, because there the consistency, where there the game is of course somewhat more complicated than in first-order logic, and the consistency property is a kind of a way to keep things organized. Now, as I said, LOAS having a winning strategy can be considered like an alternative way to think of a model. Certainly it is equivalent to consistency, and therefore it is kind of game theoretic expression of consistency. But what about Abelard having a winning strategy? If Abelard has a winning strategy in this game, then we can build a tree with so-called Beth tableau of all positions where Abelard plays his winning strategy, and we stop playing as soon as Abelard has won, which means as soon as we end up with a contradiction. Because Abelard wins every play, every branch is finite, and we can actually make the tree finite by pruning it a little bit. And we can then think of this tree as a proof of the negation. And it is actually, in an exact sense, a kind of a natural deduction style proof of not phi. So this model existence game, in this sense, builds a bridge between proof theory and model theory. LOAS wins, we get a model. Abelard wins, we get a proof. This it's kind of a bridge building concepts between proof theory and model theory. Apart from first order and infinitary logic, the model existence game can be used in the proof theory and model theory of propositional and modal logic, and the early workers certainly did this, and also currently in theoretical computer science and philosophical logic it is used. This works also with generalized quantifiers, but then what this method yields is so-called weak models, which have to be then massaged to real models by a further model theoretic argument. It can be used in higher order logic, but then again the method yields so-called general models, which then cannot be usually massaged to anything. So the general models is all we get. Also in infinitary logic, we can use this method, but what we get is what Karol Karp called chain models, so not real models. So why we don't get real models in high order and infinitary logic is because they don't have the completeness theorems that it would imply. So I would say again that this method, whichever logic you have, it's worth and usually possible to see what does consistency and proof mean in this new context. And there may be some caveats like here, but and sometimes they can be overcome like here. But I think that it is a good way to look at any logic. And as to the connection to the evaluation game, so there were these two theorems which translate from evaluation game to model existence game, and this other one from model existence game to evaluation game. Okay, now the third game, the Erfurt-Rice game. Now we have a model but no sentence. So we are looking for a sentence. But of course, to make it more reasonable, we consider two models and we look for a sentence which is true in one but false in the other, in order to have some kind of challenge. And it may be that no such sentence can be found, and then the models are called elementary equivalent, which is a very useful the theoretical concept introduced in logic and has applications in many fields, including algebra, for example. So it's a very useful concept also. But okay, so in this game, the strategies of one player, what we call LOS, track possibilities for elementary equivalence so that they cannot be separated, and the strategies of the other player track possibilities for finding a separating sentence. This was introduced in the form of a game by Ehrenfeucht, 61, but he refers to Freise as his inspiration. So therefore it's called Ehrenfeucht-Freise game. Okay, so we have two models, M and N, of the same vocabulary. This game has two players again, Abelard and Eloise, and there's some finite number of moves. A position is a finite set of pairs. I think there's a picture, yes. So finite set of pairs which are in corresponding models, like this. So that's a position. So this is a picture of a position. In the beginning, the position is empty. The rules are that first Abelard may choose some new element in M, Eloise chooses a new element in the other model, and the next position is this extension. The second possibility is that Abelard chooses something from the right-hand side model, and Eloise chooses from the left-hand side, and this is the new position. And Abelard wins if during the game the position here is such that these A's satisfy some literal in M, but the B's don't satisfy. So Abelard wins if they have some literal true here, which is not true on this side. And otherwise Eloise wins. Okay, so it does not exactly have the format of the other two games, but there is anyway, there is a strong similarity. Okay, as I said, intuitively, Eloise defends the proposition that M and N are very similar. Abelard doubts it. If it happens that Eloise knows an isomorphism, of course he can play the isomorphism. But Eloise can also win when there is no isomorphism. For example, in the empty vocabulary, if the models are big enough, it doesn't matter how big, as long as they have at least M elements, or if they are linear order, so at least size 2 to M, then Eloise can win the game of size of length M. This game, like the other games that I introduced, are determined games, as long as they are, at least as long as they are finite. It's an interesting question, by the way. Whenever we have two models M and N which are not isomorphic, how long games can Eloise win? Because one of the nice things about this game is that it makes perfect sense even if it is played transfinitely many moves. So you can play it omega moves, omega plus 1 moves, omega plus 2. What happens is that you just build bigger and bigger partial isomorphism between the models, and you can continue the game as long as there are elements in the models. So this raises the question, if M and N are not isomorphic, how long games can Eloise win? So, which means intuitively, how close can two models be to being isomorphic without actually being isomorphic? And this can be perfectly measured. In the case of countable models, it can be measured by ordinals using a so-called Scott analysis. But in uncountable cases, it can be measured with trees without long branches. And it leads to interesting questions about such trees as analogs of ordinals. I can say that at some point I think that we had in Helsinki a world record on this, how close can two models be to being isomorphic without being isomorphic, but then Sela got better results, so I think he has a world record now. Okay, so this game I claim is really a logician's version of isomorphism, and in fact, for example, as Barwise has argued, it can be called the absolute version of isomorphism. But it is, isomorphism itself is like a mathematical fact, although it's analytical, so it's not so very complicated. But anyway, it's sort of mathematical fact whether an isomorphism happens to exist between two structures, while having a winning strategy in this game is more somehow a logician's business. The other claim that I make is that a formula of logic, like first-order logic, really is this game. Again, this is a bit strong claim, but you will see when we continue what I mean by this. In some, because it is a little bit in a vague, informal sense, a formula is this game. Okay, so again, let's first look at a rather simple direction. Why, if LWAS has a winning strategy in this game, why are the models elementary equivalence? So suppose phi is for simplicity, I consider here L infinity omega sentences, so infinitary sentences of quantifier rank at most m. If we have a strategy of LWAS in this game, a strategy which examines whether they are like isomorphic or not, or whether they are very similar or not. And if we have a strategy of LWAS in this game, which suggests that phi is true in the left-hand side, model M, then these two strategies determine a new strategy of LWAS in trying to show that phi is true in N. So LWAS has a strategy to show that they are more or less equivalent, and she has a strategy to show that phi is true here. She can map these to a new strategy of truth of phi in N. This is the kind of the easy or trivial direction of the connection between evaluation game and the Erfurt-Freisse game. But even this is has some interest. I will just I will skip this proof and observe that there is a nice connection between these strategies, sigma tau and the theta sigma tau, which is reflected in connection between the sentence that we are studying and the game. If we know about the syntax of this sentence, for example, say that it's existential, universal, or positive, if we know that like in advance, then we can modify the game to reflect this by stipulating that Abelard only moves in M, only moves in N, or he has to win by finding an atomic rather than literal relation which holds in M but not in N. And so one can use this, and this is a standard use of this game, is to show that certain kinds of sentences do not exist, because as we construct two models and a winning strategy which reflects these properties, and then we can show that that a property that this model M has is not existential, definable by existential or universal or positive formula. So for non-definability results, this is a standard tool, and this is because of this connection between these strategies. Now let's go to this more interesting direction. How does a strategy of Abelard lead to a sentence? So suppose we have two models, M and N. And now we are thinking of the case that Abelard has a winning strategy. So Abelard knows how to separate these models in this game. Now the theorem says that there is a sentence indeed of quantifier rank, the length of the game. And then there are two mappings, chi E and chi A, so that if tau is the strategy of Abelard in this game of finding a difference, then chi E is a strategy of Eloise in the model evaluation game of phi in this model M, and chi A is a strategy of Abelard in the other game. So if Abelard has the strategy to pinpoint some difference, then for this phi, which kind of records the difference, Eloise has a strategy here, which can be computed from tau, and Abelard has a strategy here, again can be computed in an abstract, generalized sense from tau. And again, we can preserve the winningness. So if tau is a winning strategy, then these are also winning strategies. By the way, this sentence can be made first order if we make assumptions that the vocabulary is finite and relational. Okay, so now this sentence, I can simply write it down. That's the sentence imitates the game perfectly. Here we list the literals. So here we list the diagram, and here we simply emulate the Ehrenfeld-Kreisel game. For every x, there is some a, and for every a, there is some x. So it's a kind of doubly indexed set of formulas, and the sentence that we need is this. Now, the winning strategy of Eloise is pretty clear in this from the construction of the sentence. The strategy of Abelard is a bit more complicated, but it is still this chi A is still rather straightforward, but he has to, in that strategy, he has to use, of course, his Ehrenfeld-Kreisel strategy carefully. I will skip the proof. Again, we can see that there is a close connection between the strategy tau and the sentence that we build. Although this is the general schema of the sentence, but if tau is such that happens to be such that Abelard only plays in M, we can make phi existential. If tau only plays in Abelard only plays in N, we can make phi universal. And if he actually wins the harder game in which he finds an atomic formula rather than literal, which holds in M but not in N, then we can make phi a positive sentence. So it's not, the theorem is sort of not accidental. There is this kind of close connection. And also this game reflects, if we leave the sentences for a moment, the models, the structural properties of the models. If we know the winning strategies of Eloise, for example, or even the strategies in these component models, we can use them to build strategies of LWAS in the products, sums, reduced products, or more generally operations, so-called kappa local functions by Pfefferman. Or in finite models, one can use so-called tree decompositions and use the component strategies to build bigger strategies. Now, as I said in the case of the other two games, also here, it is pretty obvious how to generalize this to infinitary logics, generalized quantifiers, and higher order logics. Of course, the game becomes more complicated, especially with higher order logics. But the fact remains that you can define this game. And again, I would say that if you have a logic of this type, sort of in the classical framework, it's whatever logic you come up with, it's a good idea to try to see what would be the EF game for this logic, and that may reveal some things about it. The two theorems are this, which establish the connection between evaluation game and the Ehrenfeucht-Fleischer game. This and this, so Ehrenfeucht game and the evaluation game. I said that in some sense, a formula or a sentence is this game. Okay, so it's not, of course, literally true, but in fact, you can use this this type of a formula as a normal form for any formula, pretty generally, especially in first order logic or modal logic or propositional logic, and to some extent in infinitary logic also. And if you have this kind of normal form, then it really reflects the game, and that it's that sense that a strong statement has some merit. It's in a more recent development, one can develop EF game also for propositional logic, which is kind of shocking because propositional logic has no quantifiers, and this seems to be all about quantifiers. But here, the moves of the game, one moves so-called teams or sets of assignments. So it is a slightly more complicated, but you can measure the length of a propositional formula expressing some property using an EF game. You can also do this for L omega 1 omega, which is usually this game is done for L infinity omega, but for L omega 1 omega, it's more challenging because it's not determined by quantifier rank, because there are uncountably many formulas of low quantifier rank. But again, using this new idea of a game with sets of assignments, one can characterize L omega 1 omega. There's a new Lindström theorem, which I'm happy to say because the first lecture in this series by Mackay, there was a new Lindström theorem also. This is due to Celan from 2012. It has an element of delay, which I will not explain here, but as in the original Lindström theorem, also in this new Lindström theorem, the Ehrenfeucht game is centrally present. Okay, so my idea is that these three games incorporate everything important in logic. Well, truth, consistency, formula, proof, structure, the human user, and so forth. Because we may disagree whether this is a list of everything important, but anyway, these are pretty basic in logic. And these three games, or this one game, offer a coherent uniform approach to syntax and semantics. It sort of builds a kind of a bridge between syntax and semantics, and thereby between model theory and proof theory. Evaluation game and the EF game, by the way, are oblivious to whether the models are finite or infinite, and that's why they are perfectly available in finite model theory and theoretical computer science, and they are used there as we speak. I claim and announce that there's a lot of potential for the study of the interaction between these three games, and that I have given the name strategic balance of logic. Thank you very much.
Thank you, Professor Väänänen, for this very nice talk, which I honestly really liked, but okay, doesn't matter. We have our silent applause because these are the rules of Zoom in a sense. So thank you very much. And now we are so people are applauding. So now we open to questions. So if someone wants to ask a question, that's a good moment to do it. Just unmute your mic and ask the question.
I asked it in the chat, but you mentioned compositionality of the first class of games, various operations that you could perform which give valid games and where these games depend on one another. Is there a nice notion of morphism of games, and do any of these classes of games form nice categories? For example, if you fix the fragment of logic that you're working in, can you get any nice categories out of this?
I think so. I know that Samson Abramsky and Anush Damar have some recent papers on a category, on this kind of morphisms and categories. And it's not maybe exactly the same, so my functions here, but I think that there is a room for a category theoretic thinking here, which I am not an expert myself on that, but I hope that maybe I can interest some people to think about it. But what I said about compositionality is, of course, I refer very, very vaguely and briefly to so-called game semantics for example, for linear logic or programming languages, which Abramsky has, for example, at Plus contributed to, and where they can obtain kind of compositionality using games. But it is, I am operating here mostly on the level of having a winning strategy, this kind of propositional, having a winning strategy rather than the games themselves. But of course, because I'm interested in having a winning strategy, I have to understand the games and I have to take the games seriously. So I'm totally open to identifying the meaning of the truth or consistency or formula to identifying it with the game rather than the proposition that player 2 has a winning strategy. And I think that gives room to kind of category theoretic analysis.
Thanks.
If I may ask a question which is connected to Morgan 1. In fact, I have in a sense the same question, but on another point of view. So what I didn't understand in your presentation is what kind of game you are identifying. So if we look at this from the perspective of just game theory, the kind of games you describe are a very special class of games. But do you have in mind some kind of axiomatization of what games you are ranging, or for the moment you just have a translation that eats a logic and spits a game?
Yes, it's a good question. I don't have in mind here like a general concept of game, although when we have studied in my group transfinite erfolgreiche games, we developed some general theory of comparing game comparison to how to compare two games, but these games tend to be always a perfect information, two-person zero-sum games, and of course that's a very limited concept of a game. But I know, and I appreciate that a game theorist listens to my talk and, oh, that's very, very special games. He's misusing the word game. Okay, maybe not misusing, but anyway, I take some concepts from logic and I put them, or my predecessors put them in the form of a game. But these games are, in a sense, very special. What I emphasize here more is the connection to logic than the connection to game theory. But I know that, for example, Johan van Bentem has, I think, written a book or two books recently where he is more liberal about games than his games and logic, and he tries to find the logic of games in general. This is not my approach here. I'm trying to use games in logic rather than logic in games. It's my limitation.
Could I say something, Ivan?
Of course, I mean.
Okay, so it is something that is so obvious to Jouko, so perhaps I felt that maybe he did not emphasize it enough. But what I find very fascinating about this is that these methods allow us to study logics that cannot be studied by inductive methods. So in fact, first order logic you can take as an example, where you can do game theoretic definitions and you can do classical Tarski-Watt definitions, and you have this equivalence, and it's all very nice. The Erfolgreiche strategy game is also about first order logic. But when you move away from first order logic, either by going to strong logics where you don't have completeness, or going to weak logics which study finite models, then the inductive definitions no longer make sense, or they fail at the very first step. So in fact, that these games are the only method that allow to study logics in some sense. And in fact, this logic that Jouko mentioned at the end, this logic of Schellach, L1 kappa, in a sense was revolutionary, because he didn't introduce this logic by any sort of syntax. There is, the syntax is a consequence of the game. The logic is introduced by a game. And because the point is that he wanted this Lindstrom theorem and realized that this is the game that carries it. So I think there is not only a beauty of these methods, but there is also a really genuine strength, which allows you to do things that you couldn't otherwise do. So this is just a comment.
Yes, it's absolutely true. And in infinitary logic, a very powerful tool, like syntactically, was so-called game formulas introduced by Watt, for example, and Kicker, and so they don't have the form of the traditional infinitary logic which was introduced at that time, except that they have so-called approximations. But what was kind of the starting point was a game formula, and the game formula, of course, the starting point was the game, the Erfolgreiche game. So it is true that in some directions it goes deeper and it's easier to work with than trying to formulate a language. And in fact, as Mirna said, Shella has this new infinitary logic, which has no syntax at the moment at all. And it has just the Erfurt game. But because of the properties of the game, he says, Shella says that there must be a syntax. It doesn't matter what it is, because he has a Lindström theorem. They are all equivalent. Whatever syntax you come up with is an equivalent to any other. So the syntax sort of disappears into the horizon. So in that sense, maybe I would indeed, as Mirna said, these game theoretic methods are maybe more go deeper than the method of trying to formulate languages.
While people decide whether they have other questions, I just wanted to clarify that I didn't mean that this game that what you like. I don't see a limitation as a limitation. The fact that that the class of games you describe is small. I see it as an opportunity, and so that I asked it because I think to describe more precisely this class of games that you get could be useful in the analysis. So it was not mine was not a comment saying this is not game theory, but mine was a comment of a good description of these games from a game theoretic point of view might be useful. That's what I meant.
Yes, I understand. Yes. I would like to ask Michael Mackay a question. You are muted.
Okay.
Okay.
All right.
Okay. All right. Because about the origin of the method of consistency property, how did you come to make such effective use of that? Where did you sort of learn the consistency property?
Well, I read Smullyan. That was it. And I already lectured about consistency properties in 1966 in Berkeley.
Mm-hmm.
In Berkeley, in the academic year 66-67, I gave a two-term lecture on model theory, apparently the first systematic lecture on model theory ever, and there I already talked about it. So in 66, but the source is simply Smullyan, as I actually said it in the title of my paper, which appeared in the Polish journal.
Fundamenta.
In the title of that paper, I used Smullyan's name.
Yeah,
that's the origin.
Smullyan has this certainly the concept and the name, but his thinking is not very moral theoretic.
Of course, yeah.
He's more trying to. He's thinking more in a kind of proof theoretical or a uniform approach to interpolation and completeness and this, but I think that I saw it first in Kiesler's book on infinitary languages, but that was after your lectures.
Yes, I think the first paper which explicitly uses and displays the method in infinitary logic is my paper in the Polish bulletin.
Oh. Bulletin of the Polish Academy of Science.
Yeah, right. Yeah.
Okay. Yeah, that's a difficult bulletin to. When I was a student, as Mirna said, in the early 70s in Poland, and then one of the benefits of many was that I could get all the bulletins that I wanted by going to the library. But nowadays it's because it's not scanned, so it's not so easy to get. But yes.
Do we have other questions from the audience?
Do you allow me to make a short remark?
Yes.
Of course.
So
it would be a crime not to.
what is sort of relevant for me is that all this game theory for logic relativizes to faults without any problem. And it's here the importance is not just that the syntax is sort of sufficiently complete for faults, but the faults equivalence is a perfect substitute for isomorphism. And so when you make these translations and replacements, everything fits.
Yes. Yes.
So the Lindström theorem for faults is an example.
Yes. Yes.
Okay, so I thank you, Professor Mackay, and of course, thank you again, Professor Väänänen, for your talk and for the discussion that came after. And I would say for today, we are done. I will stop the recording now. Thank you, everybody, for joining.